So today we're going to talk about star clusters. They're really important in the study of astrophysics and astronomy, and so we need to have a good introduction. So what are star clusters? Well, basically they're groups of stars, as you might think. The important thing is that they're held together by their mutual attraction. So you think of it as being, like you think of the sun and it holds all the stars, all the planets in orbit. If you've got a pair of stars, they can orbit around each other. We talked about binary stars. This is where you have a whole system of stars, maybe hundreds or thousands of them, that are all orbiting mutually. And in order for that to happen, they have to be born at the same time, just like the solar system. It's very hard to capture a star. Things are moving too fast around each other. And so in order for them to be held together that way, they must have been born that way. Now, how do we know that? How do we know that they're gravitationally bound? We're looking, we have no depth perception. We want to be able to figure out whether these stars that look really close together are actually associated. Well, we can look at their relative motions. If they're moving around a common point, a common center of gravity, then they're bound together. But how do we measure that? How do we decide how they're moving? Well, there's two different things that we need to look at. We've got the motion that we see, which is transverse. That is, we might have a star that over the course of a few years appears to move very slightly. Now this is distinct from parallax, because in parallax it's moving backwards and forwards according to our position. Whereas this is something where, relative to the background stars, even at the same time of year, it's moved a little way along. You also have motion in a radial direction, either towards us or away from us. And so the true motion is just the vector sum of those two. And we can measure this tangential velocity by looking at how they appear to be moving. We need to know how far away they are for that to be a true measure. We can certainly measure the angle they move through, and then if we know the distance, we can work out how far they've really moved and in what time. So we've got that speed. We call this proper motion. Strangely, it's not the proper motion in the sense that it's not the true motion of the star, but we call it proper motion. Don't get confused. And then the line of sight, we can use the Doppler effect. So if it's coming towards us, it's going to be blue shifted. If it's moving away from us, it's going to be red shifted. And that's where we can figure out what the true motion is. So here we see a picture of the Alpha Centauri system. We've got these three stars, and it's about 1.3 parsecs from us, and it's moving in a direction that's not quite towards us, but it's got a transverse and a radial component, and its true speed is about 30 kilometers per second in that direction. Okay, so we've measured how these things move, and essentially just used Pythagoras to stick it all together as a vector equation. But then different stars that are in a constellation, if they're not associated with each other in a cluster, then they may be moving different ways. So here we see the Big Dipper, part of Ursa Major, and we can see here that the brightest star here is moving in this direction, whereas the next star is moving in this direction. So we've got all of these different stars, and they're moving in different directions. So over time, as they move in their respective directions, we're actually going to see a different shape. Now this happens over thousands, billions of years, and so it's not something that we're going to witness over the course of our lifetimes, but we know that they're going to change. Okay, so let's go back to our clusters. There are two different types of clusters. We have open clusters, so Pleiades is the classic. It can be seen naked eye just about near Orion, and it's an open cluster. That is to say, it contains about 1,000 stars. It could be a few hundred or a few thousand, and it tends to have, you can see in this image, that there's this diffuse nebulosity, this blueness. This is dust that is scattering the light from the stars. It's blue for the same reason that the sky is blue. And this is what we're looking at, where the dust is actually what's left over from star formation. We'll get on star formation very soon. These star clusters are composed of population 1 stars. If you remember what we did in metallicity, population 1 stars are relatively high metallicity, like the sun. These things, we find them in specific places in the galaxy. So just like we have metallicity gradients, we also have places where we expect to find clusters like this. And these seem to be where you get lots and lots of stars. So this is in the spiral arms. We're not finding them all over the sky, but in specific places where there are already lots of stars. These don't tend to have very long lifetimes, so they are bound to each other, but they're dispersed enough, they're far out enough that it doesn't take that much pull from outside to pull them apart. And so what you have is that as this cluster is moving around the galaxy, it's going to come close to other stars and other clusters, and that's going to have little tugs on the members, and some of them are going to break free. Some of them are going to be given enough of a pull that they no longer are bound. And so these are systems that will break up fairly quickly, and this is probably where most stars are formed. So the sun would have been formed in a cluster like this, and then over time on the journey around the galaxy, that cluster would have been fallen apart, and so it ends up as a field star. Field star is the term we use for a star that's not in a cluster. So this just explains what I just said. We've got escapes that are due to velocity changes, and that's basically where, as you're going past something massive, you're going to get pulls on all of them, but because of the 1 over r squared effect, the stars closest to whatever is pulling them, whatever mass is there, are going to be pulled more, and eventually they get pulled out of orbit altogether. So, basically it takes a couple of 100 billion years for the sun to orbit the center of the galaxy, and it takes about that much time for a star cluster to fall apart. So there are a few that are older, but they're very rare. And so these are all just field stars that now, like the sun, are just out there, but they would have been born with some brothers and sisters in an open cluster. And so here we see the Pleiades again. You can see this is also called the Seven Sisters, although actually only about 5 of them are really strongly visible to the naked eye. And here we see its HR diagram. So you can see here it's got a main sequence, but it doesn't seem to have much else. We'll come back to that once we've talked about the other type of clusters. The other type of clusters are globular clusters. We can see here Omega Cen, and they're very densely packed. They have tens of thousands to 1 million stars, and they tend to be either in the bulges of galaxies or our galaxy, or in the halo, that is above or below the main disk of the galaxy. We can see from the spectroscopy of these objects, that the stars, that they have much lower metallicities. They're generally population 2 stars. And that makes sense in terms of where we see them. They're found where there isn't much star formation going on, either in halos or in the center of the galaxy. And so they're expected to be very old because they're containing things that don't have high metallicity. And here we see Omega Cen again, and its HR diagram. And you can see it looks quite different. In this case, we've got a main sequence, but we've only got about half of it. We don't have the upper half, we only have the lower half. And then we have this branch off here, and it looks like we've got a bunch of red giants. And so it's actually these, looking at these and seeing what stars are there, that helps us understand the evolution of stars and the timing of them. So here I've got the two again. I've got the Pleiades and the Omega Cen, and we've got the comparison of their two HR diagrams. And so we can see here, this has got all of its main sequence, but it doesn't have any red giants. And this is something that we think is relatively newly formed because of the metallicity. And then here we have one that's got much lower metallicity. We think it's much older, and we don't have much of the top end of the main sequence, but now we have lots of red giants. And in this case, we have something that we can then define how old they are. And so the Pleiades is considered young, and Omega Cen is considered old. And so here we've got those two compared again, and let's talk about this from the point of view of the populations that are missing. So when you've got a young cluster, you have no red giants. And you have lots of red giants in these old clusters. And again, this age idea is based on the metallicity. And so it implies that the red giants are older than the main sequence stars. So we think that they must evolve that way, right? You've got things missing here. That's because they've already evolved into something else over here. You also see all of the different types of main sequence. So from the cool to the hot, all the main sequence stars are represented on the main sequence for the young object, for the Pleiades. But if we look at the Omega Cen, it's all missing here. And so that also implies that that's where these ones came from. And so it tells you something about the speed at which different things evolve. So even without knowing where the energy is coming from and applying that, it says that those high luminosity stars are evolving faster than the low luminosity stars. Now this isn't based on just these two, it's based on hundreds of clusters that have been studied and looking at the difference between them. But this is where we get our initial studies of what's going on with the evolution of stars. So I'm going to bring you another one here. This is the Hyades. And so here you can see it's got a main sequence. It's got quite a lot of main sequence. It's got a little bit of red giants up here, and it's got some white dwarfs. So how do we classify this? Well, it doesn't look like the Pleiades in the sense it does in the one way because it's still got most of its main sequence, but it's missing this top end, and it's got some red giants. But it doesn't look like Omega Cen because it's still got quite a lot of its main sequence up here, up to 10,000 Kelvin stars, and it doesn't have nearly as many red giants. And so this implies that it's somewhat intermediate. It's older than the Pleiades because it's already lost its highest mass stars and they've gone over here, and it's younger than Omega Cen because it's still got these stars. And so this is something that we can then use to determine the age of these things from where this says turn off. So you've got the main sequence, and over time the main sequence should get shorter and shorter, and it should turn off at lower and lower points, and that should tell us how old it is. Okay, so here I've got, and we call it the zero age main sequence. This is because when a star hits the main sequence, it still evolves a little, and so this is its first entry onto the main sequence. And here you can see that if this is time zero for a cluster, actually what we've got is that the high mass stars are on the main sequence. Our low mass stars haven't even got there yet. Stars form from clouds that collapse, and these things haven't got to the point of fusion yet. They're still clouds of things that are glowing because they're really hot, but they're not actually, it's just gravitational collapse that gives that heat. And so these are not even stars yet. So it takes longer for these stars to get to the main sequence than it does these stars. And remember, this is HR diagram, so this is luminosity and this is the spectral type. Okay, so now we're a little bit further along. This is 10 million years in, and now the top end, our very hottest, brightest main sequence stars are already moving off. They're somewhere over here. And we haven't got our coolest, faintest stars into the main sequence yet. They're still protostars. At 100 million years, now our main sequence cutoff has moved down a little further. We've got a few more stars over here, and now we've got pretty much all our stars are actually stars. They're not protostars anymore. We keep going. At 1 billion years, everything is definitely on the main sequence, and now we've got all the stars that are brighter than about 100 times that of the Sun are already dying. They're already off the main sequence. They've stopped doing whatever it is that they do in the main sequence. And then here you can see at 10 billion years, which is basically the age the Sun will stop being a main sequence star, we've lost all of these main sequence stars, and we populated this red branch region. Okay, and that's what keeps happening. Eventually we'll get rid of all of these, and they're all going to be up here or down here in the white dwarf section. And so I just want to show that all at once together, partly because then it shows up on PDFs. But this is how you can then work out from plotting the HR diagram for a cluster how evolved it is, how far along it is, how long it's been around. And this allows us to then look at what that means for the timescales of evolution and how metallicity affects it, because we get the metallicity of these things. Here I've got an animation that I'm going to show you, and this is kind of showing you that main, so we've got a main sequence here, we've got our very hottest stars and our very coolest stars, and they're already on the main sequence. So this is where even the Sun is already on the main sequence, we haven't actually got the lower ones on here. And so it's just a HR diagram, and we're going to watch how it changes over time. And you can see how it's got an age, it's going to populate it. Remember, we get the masses of these things from ones that are in binaries, so we know that this is the mass sequence. And to start with, we're going to go in short steps. These are 200,000 year steps. And very quickly, those stars that are at the very brightest, they're 1 million times the luminosity of the Sun, they evolve over here and then they explode. These are things that just disappear completely. Some of them get as far as being red giants, and then they'll explode and disappear. And you can see very quickly, we're not even at 10 million years yet, and we've lost most of the top of the main sequence. This is all the O stars. Now we're taking longer steps, and we've got 45, 50 million years, and we're starting to lose the B stars now. So our B stars are starting to disappear, but see, it takes longer and longer each time. And they all end up somewhere over here. But each time it takes a little bit longer. at this point, there's still things that are probably going to explode. Now we're going in bigger steps. This is 0.2 billion years. And you can see that at this rate, they're disappearing pretty fast to start with, but then we're at basically the age of the Earth now, age of the Sun, and the Sun is still quite happily down here, and we've lost all of the others. And so when we look at a cluster, we can tell from what main sequence is left how old it is. Okay, so this main sequence turn-off, basically we can plot different clusters. So this is showing you what the main sequence, and then if they have a collection of other stars over in the red giant branch, you can kind of put those down too. We've got the main sequence is shown on here in terms of where these different clusters are. So this is the Pleiades here, and then here we've got the Hyades. Remember that was a little bit older than the Pleiades, but younger than Omega Cen. I don't think I have Omega Cen on here, but you can see all these other ones. And so we can basically work out from where the turnoff is how old it is. Now you've got to be a little bit careful. So here we've got the Pleiades. So the Pleiades are only 100 million years old, right? Because it's lost all of these stars and it's basically not got anything over here yet. But when we get down to the Hyades, that's at more like 1 billion years old. So it's turning off here, and the Hyades is going to have some more over here. Now, if we look at H and Kuiper, this is weird because you can see that you've got a lot of this top end up here and not much over here, and it's all the way up here. And so H and Kuiper, these are red supergiants. It really has only lost the very most massive of its stars. Whereas if we go look at this one, M67, that's a really old one. It's basically, about the age of the Sun, more or less, and it's already got its big red giant branch. So we've got more massive stars evolving more quickly, and the hot and luminous stars are dying more quickly. And in the oldest clusters, they're only going to have the lowest mass stars, but a young cluster can still have its high and low mass stars on the main sequence. So this is just a close-up on that in case you wanted to see it more clearly. And these are the ages. Oh, sorry, backwards for some unknown reason. And now the last thing I want to talk about is the idea of main sequence fitting. So here I've got, this is a plot. I've plotted an HR diagram. I've got luminosity and I've got temperature, and these are a bunch of stars that I've observed in a cluster, and when I plot them I get a bunch of them on the main sequence and maybe some red giants over here, and I've just plotted them, and I don't know how far away it is, so I don't know how bright they really are, but because they're in a cluster I know their relative brightness is, so this just has to be relative brightness. This can be the apparent magnitude. Now if I compare this to, oh no, wrong way, if I compare this to a regular HR diagram, I can see I'm offset. My main sequence is too low and my giant's too low. And so basically I want to shift this up so that it matches. And when I shift it up so it matches, so now I've got a main sequence that's in the right place and my giants are in the right place. Now I know how bright it should be. So from how bright it appears to be when I first observed it to how bright it really needs to be, I can work out how far away it is. And so it actually ends up being a standard candle. It's one of the ways in which we determine the distance of things. And so we can use clusters in other galaxies as another way to measure the distances to them. But this also means that we can then use them for, we don't even need to know the distance in order to start studying them. And so what we get from studying a whole bunch of clusters is that we end up with a measure of how stars can evolve. So this is showing you the path that we expect for a star like the Sun. So I've got what the main sequence would be for all stars, and then you can see under here there's a whole bunch of stars plotted on here. And here's the Sun. So it starts here, it evolves a little bit, so this is where it is, and in another 5 billion years or so it'll be here, and then it's going to become a red giant. Oh, it's going to do it every time. And then a yellow giant, and then it becomes what's called an asymptotic giant branch star, which we'll come back to. And then as it's dying, it becomes a planetary nebula, and eventually a white dwarf. We're going to go through how we get through all these steps. And that's going to be our next topic after class as a medalist.